Raghavan, Secretary of IIT Madras Alumni Association, batch of 91, to please give the official welcome. Over to you, Sridhar.
Thank you, Nishani. Glad to be here. And first and foremost, thank you for Gopal for inviting a lot of distinguished people to these Guru Talks. And these Guru Talks are an important component of what the IIT Madras Alumni Association is giving to the alumni in the sense that it contacts well-known, renowned people and asks them to talk about research in their fields or even latest topics in a manner that is possibly reaching a lot of alumni who are not technically inclined in that way. And in that regard, I'm really glad that we have Professor Aravind Srinivasan from University of Maryland, College Park. He is an alumnus from 1989 in computer science, Gopal's hostel, Alakananda, I believe. And he went on to do a PhD in Cornell by 93, 4 years. That was really quick. And then his research interest has been into algorithms, probabilistic methods, and then some of the hot topics of the day, which is machine learning, data science, artificial intelligence, and so on. So we are really glad that we have a person of this repute to talk to us about the very interesting topic that he has chosen for today. He is currently a distinguished university professor at University of Maryland, College Park. Dr. Srinivasan is also a distinguished alumni of IIT Madras and fellow of ACM, IEEE, AMS, and lot more. Just like a doctor, he's got a lot of credentials. Without much further ado, I welcome Professor Arvind, and let's all hope for a great Guru Talks. Thank you so much.
Thank you very much, Sridhar, and please call me Aravind. It sounds too stuffy to be called professor when I'm talking to fellow alums, but even
That's
otherwise.
okay. That's okay. Thank you.
Thank you again. So,
Yeah, Shrikant. Yeah, I am still. I will call you back. Thank you so much.
So I'd like to start by thanking several people. Most importantly, all of you. I know that Friday is not the best day to attend, and thank you for kindly attending. And I hope this session gives you something. There'll also be time for questions at the end, so please feel free to ask. Like was mentioned before, this was really initiated by my good friend Gopal, who's here, Srinivas Gopal. He was my hostelmate and 1 year junior to me. And he really initiated this and has been doing a lot of work with Guru Talks. But of course, he didn't ask me to say the following, but I would like to say here that in addition to being an entrepreneur, he does a lot of public service by making direct payments to, several, lower income kind of people who get into difficult situations. And, it's just, really great to see his range of activities. Thank you, IIT Madras Alumni Association for making this possible, and several of you here who have worked quite a bit to arrange these talks. And of course, our beloved alma mater, IIT Madras, to which we owe a lot, and with which institution we have many good memories. And last but most, I'd like to thank the Indian taxpayer. I think all of us alums, without being boastful about it, objectively got a high quality education at near zero cost. And when I think about it, in the 80s, there weren't that many, educational loans and so on easily available in India. And if the cost was sort of even somewhat comparable to the quality that we got, my family wouldn't have been able to afford the education. So I'm deeply grateful to the Indian taxpayer as well. So so maybe I'll say something very briefly about myself, since this is not like a regular talk, but more one among friends. But very briefly, like was already said, so I got my degrees in 89 and 93 at IIT. I was in Alakananda hostel. I work at the University of Maryland, and I'm also what is called an Amazon scholar with Amazon. I am fortunate to maintain close links with IITM and with several IITM alums, including, of course, my hostel mates, but many others. My areas of interest are these. I'm more interested in foundations, algorithms, the role of probability in computing, which is actually a remarkable story starting the 1960s, and also data science and machine learning. Interested both in the fundamental theory, but also, as all of you very well know, the exciting applications are so many. Just for example, if we take, one domain here, health, my collaborators and I, in fact, several from IIT Madras, actually, several IITM alums, one area of interest has been computational epidemiology, and as we all know, it's been of substantial interest in the recent past, and unfortunately will probably be in the future as well. And the other is in genomics and so on. For example, cancer genomics, there is there's the true possibility of personalized medicine and so on. So, I mean, we are at a very fortunate time where good advances are possible. And the point of this talk is that, there are, significant fairness issues also that we have to very carefully consider. So, we'll go quickly over this. Let me not read out everything on the slide, but I'd like to point out some things that are, once we see them, they seem very clear that indeed that these are things that we have to, place emphasis on, but which may not a priori have been clear. So I hope that I hope to be able to bring these out. The role of probability is actually quite interesting, in my opinion, and I'd like to bring that out in the form of how stochasticity can help both with individual and group fairness. So overall, I'm personally optimistic that with careful human plus AI interaction designed very carefully and adaptively as it evolves, we can get truly not just utilitarian solutions that kind of help a large number of people, but which are also fair and don't disregard various stakeholders. Okay, so this is the broad outline, right? And as we all know, you can call it AI or algorithmic decision making. I will, as you know, AI, of course, is a very broad phrase these days. For the purposes of this talk, I will focus on those domains where humans are impacted. And as you know, for instance, my friends who hold senior positions in the tech industry and in other companies say that routinely it is AI, of course, that does initial filtering of resumes and so on. Right. So now even here you directly get the question, have we vetted the AI enough? On the one hand, could it have biases inherited from humans, for instance, who may have implemented the AI system, or could it have biases that we weren't even aware of? Right. So that's a possibility. Right. So but this is effectively happening almost across the board, and loans of various forms. And of course, the news and ads that we see are highly curated to our internet activity, highly connected to our internet activity. The criminal justice system, where I think there are actually exciting possibilities. I hope to say something briefly about this at the end. Medicine, of course, in personalized medicine and so on. Right. So effectively, as many of you may know, so now essentially what these systems do is there is a living, breathing human, and they are boiled down to, in this case, to what you may call a feature vector. In the simple case, so suppose you're interested in some medical domain where a few important characteristics of the person are, I mean, their name, for example, is not very important. Their social security number is not important, but perhaps their age, their occupation, because if the occupation may exacerbate their health condition, their race certainly could be important, and gender, and say current medication. So I've just taken four sample features, but really a human in this case, again, of course, AI goes beyond humans, and as you know, one of the very exciting one of the exciting and maybe worrisome also trends that we expect to see is what is called agentic AI, where there'll be many more AI agents than humans. But let's set that aside. For the purposes of this talk, we think of a human boiled down to what is, in this case, it's a four-dimensional vector, right? Their age, some of the entries are numerical, like age, And in this case, many are not numerical, like race, for example, the current medication they're taking, and so on. But in any case, so you boil a person down to a range of very highly relevant features. In this case, we only see 4, but in practice, these would be in the hundreds and perhaps even in the thousands. Excuse me, I see somebody in the waiting room. So yeah, please take care of that. So yeah, okay. So this is the domain that we're going to be talking about. I will first speak about 3 episodes that were brought out both in the scientific literature and some in scientific and technological newsletters, and view them as starting points for a discussion on fairness. Right. So here are some non-exhaustive principles that we may wish our systems to follow. For example, that similar people should be treated similarly. There is a very famous paper of Cynthia Dwork and others. Cynthia, by the way, she's a professor at Harvard. Most recently, she won the National Medal of Science. So she and others had this influential paper around 2012, where, among other things, they put out some such desiderata that you may want. For example, a natural notion of individual fairness is that if I see somebody similar to me with qualifications or whatever conditions appropriate to a certain AI decision-making system, then the outcomes that we see should hopefully roughly be similar. And of course, we want opportunities to be available to everyone. And also, of course, errors are inevitable in any system, human or otherwise, right? So what you may want to minimize is, for example, say, in a setting where getting a negative is not a good thing, like in, for example, college admissions or job applications and so on, right? The false negative rates should be roughly the same across different demographic groups, for instance, right? So in other words, if a demographic group has size, say, 500,000, and the number of entities, a number of people from the group who get unfortunately falsely negatively classified as 100 in a group of 500,000. So then in another group of a size about 1 million, which is twice 500,000, we would like ideally the number of false negatives in this case to roughly become twice that, right? So in other words, the rate of error, in this case, false negatives, should be roughly the same across different demographic groups that you're serving, right? And similarly for false positive rates, for example, you don't want to be falsely audited for taxes when you've been paying your taxes properly and so on, right? So in general, yes. So a natural point to make is that just carefully crafted algorithms alone are not the answer, and that the societal context is something that we have to take careful consideration of. Let's see 3 examples recently from from in the over the last 10 years or so. The first episode is there is a very nice paper in Science from 2019 about how an algorithm that was actually being used for millions of US patients across large healthcare systems was actually producing racially biased results. And the second is very recent. The UK actually, as you know, kidney transplants and so on have been around for a while, but one of the exciting frontiers in organ transplant is liver transplants. So this AI snake oil newsletter or blog, it has this interesting article, and we'll talk about all of these and what the issues here are in a few minutes. So whether this system systematically excludes younger patients. Another slightly older, but not that much older, 10 years old, is this paper from Carnegie Mellon, where they pointed out that in around 2014 or 2015, in your Google settings, in your Google ad settings, you could add your attributes like female, like gender, and other attributes, right? So what they found in this work was that if you set your gender to female then, 11 years ago perhaps, right, then in general, statistically, you got fewer ads for higher paying jobs, right? This in fact, of representation, maybe of the three issues we bring up, this may be the most easily formulated and solved, although again, not trivial. And all these problems are important, of course. And nobody is claiming that the people or organizations who designed these systems had any intentional bias. But the question is how to fix it in future, also avoid such events, right? You don't want to just reactively fix these, but how can we be proactive in sort of designing systems from the bottom up that involve humans and the power of AI and algorithms very effectively, and maybe do their best to avoid biases like this. So please keep these three in mind. We'll start with E1, right? So it's the following. So if you look at the chart on the right, right. This is US centric, but I think in much of the industrialized world, this is probably true. A significant, if not quantitatively, qualitatively, the numbers will probably be true of large countries like India as well. Right. So which is that, almost all the healthcare expenditure, goes to, a very tiny number of people and situations, which is for high risk care management, right? So a lot of people routinely fall sick and so on, and then the expenditure is not much, but a small number of high risk situations, of course, contribute to much of the healthcare expenditure. And as you know, the per capita expenditure in the US is very significant in the health domain. Right. So essentially, because significant additional resources and attention are needed for when the situation is very complex, therefore, many large US health systems naturally, what they do is, so they want an algorithm or system that can help identify candidates for this notion of high risk care management, right? In other words, if you can proactively flag a person who's maybe not even your patient yet, that they may develop very significant conditions in the near future that may require substantial resources, why not get them into your system right away, and then start with whatever aggressive treatment they require, right? So basically this and indeed this algorithm that was studied by Overmeyer et al., it assigns every patient or potential patient a risk score, right? So, and of course, the higher your risk, the higher your probability that you'll have to, incur very significant costs in the health costs in the near future, right? And what the paper shows is that, right? So if you take, so basically, if a person's score on a scale of 0 to 100 is, let's say, 90, that means that they're in the 90th percentile of risk. Okay, so very close to high risk, right? Very high risk, right? But what the paper systematically found is that if you take two typical people getting roughly the same risk score, say 65, right? Then statistically, and again, not at the level of individuals, but statistically, a Black patient getting a score of around 65 was significantly less healthy than a white patient getting the same score, right? So which means that if you think about it, essentially a Black patient with a score of 55 from the system is probably roughly as likely to incur high costs as a, let's say, white person with score 75, right? And of course, since it's only the higher score, patients who will get flagged into the system, this person at 55, in fact, is less likely to get flagged and therefore incur high costs and so on. Okay. Again, nobody is claiming that there was any intentional discrimination, but this was indeed found, right? So what was the reason, right? So so one of the authors, Sendil Mullainathan, he was at Chicago Booth then. He's at MIT now. You can read this simple short review from Chicago Booth, and but of course there is the paper available as well. Right. So so essentially, what is these are some charts from the paper, right? So essentially, the key simple point was that the objective function used was wrong, right? So your future healthcare needs are not that trivial to boil down, right? So what the algorithm used as a proxy for your future healthcare needs or expected, health expenditure was what they call future healthcare costs, right? So the risk scores is essentially your algorithm's prediction of your future healthcare costs, right? So that's it, right? So the objective, what they view as the risk is simply their calculation of the person's future healthcare costs, which is calculated by some machine learning system, right? Now we'll talk about the notion of calibration again in a few minutes, but the algorithm is actually well calibrated, which is that if you really want this as your objective, FHC, then the FHCs of Black patients were statistically similar to that of white patients. So there was no issue there, right? But the point is the societal issue in the US is that typically, due to various socioeconomic, reasons and reasons of geography and so on, Black patients, typically are, often less likely to receive treatment. So your machine learning system, of course, looking at their past behavior and incurring of costs, right? Since they've generated lower costs, it also flags them as having a lower FHC, right? So basically, yeah. So therefore, again, two patients got the same score, 65. It was not at all the case that their real risks were the same, because your machine learning system, what it learned from to estimate the proxy FHC was past healthcare expenditure, which is not socioeconomically very balanced in the US, right? So this sentence from the paper is quite interesting. Essentially, it says that very reasonable looking choices can actually lead to the bias creeping, right? So the good thing is, the paper's authors and the algorithms manufacturer, they agreed to work together. I don't know what the current situation is, but what the science paper at least says is that by working together, they could, for example, by getting sort of better handle on the output, right? And including simple things like the number of active chronic conditions, they could, according to one measure, reduce the bias by, say, 86%, right? So again, this paper was written in 2019. I don't know what the current situation is, but what I wanted to point out is there is an interesting thing that, so for instance, if you have an automated system to give home loans, right? So it's of course illegal to discriminate based on race or gender or other such characteristics, right? So what you may want is that the algorithm that takes the potential buyer's features, the feature vector, should perhaps hide, say, these protected features like gender and race and so on, right? So while that's a reasonable thing, in fact, what papers like this point out is that the objective not being very well immersed in the socioeconomic context is perhaps an even bigger issue, right? And it's a warning on unintended consequences, like I mentioned before, right? Okay, so let's look at a different episode, right? This is from this very recent blog post from the AI Snake Oil newsletter, and I'll mention the book, the AI Snake Oil book at the very end, right? Okay, so yeah, so in effect, what was found is that this system that was rolled out, the UK centralized its liver transplant system. Previously, it was several regional systems and so on, and this was centralized. And after the centralization, it was found that, so what you see here, which is that, actually it seems to, again, unintentionally seem to discriminate against younger patients. The question is why? And the answer turns out to be very simple. Okay, so right now, what the goal of the system is the following, right? So is to, for every patient P, give them what is called a transplant benefit score, right? So a TBS. And how is it for a specific liver, right? So suppose this liver is ready to be transplanted, right? And you have a patient P, then with respect to both P and this specific liver, let's calculate the following simple quantity using machine learning with some predictive model, right? So which is the difference of how long patient P would live if they were given that liver, right? Minus how long they will if they did not get a transplant, right? So that's the notion of utility of that liver for that person, right? So on both of these quantities, how long are evaluated or estimated through some predictive model, right? So, and of course, then if you can estimate this TBS very well for every patient liver pair, you can just do the following. For a particular liver, you can do the following. you can sort the patients by decreasing TBS, right? In other words, offer this specific liver to the patient who's been estimated to be the most relevant in terms of TBS for this liver, right? And offer it to them. But for various reasons, people may decline, right? If they decline, then move down your list, right? There was the person with the topmost TBS. In case they accepted it, go forward with the liver transplant. If not, if they decline for some reason, come down to the next person in your list in terms of TBS, highest TBS, and ask them and so on, right? So it seems like a very reasonable thing, right? So what's to complain? In fact, it seems to favor younger patients. Why is that? Because if you look at the difference here, right, the first one obviously is probably will be much longer for a younger person, right? So a younger person would probably live much longer given that specific liver as compared to say somebody who's 30 or 40 years older than that, right? So in fact, one may say that on the face of it, maybe does this discriminate against older patients? But actually, what was found is the opposite, right? So what happens in practice, and we'll see why in a minute, right? So each of these two likelihoods of surviving with and without, right? That's unfortunately not what is evaluated. Again, the objective function is not what you originally started out with as an aspirational goal in the TBS, but instead you try to estimate, again, for a given patient P and a given liver L, what is the likelihood of P surviving 5 years with this and without this, and take the difference and use this as a proxy for the TBS, right? So why is this done, right? Now, first of all, before seeing why this is done, now we obviously see why this can be biased against younger patients, because for the with and without terms, a younger patient has a higher without term, right? Because a younger person is typically more healthy, right? So even without the liver, maybe they have some expected, the probability of surviving 5 years is maybe say 60%, while for an older person it is say 25%, right? So therefore, since you have a difference of two terms where maybe the first is roughly similar and the second is larger, therefore younger patients actually go down the list, unfortunately, right? So, but why did they use this 5 years as a proxy? It was simply a data problem, right? The data availability. So essentially, this length of follow-up was selected, right? And longer follow-up data was not, right? So very often we cut corners and use what data we can. And here you see a serious issue of, in a pretty major healthcare decision where, a segment of the population can be impacted. Right. So in fact, these authors also have this nice paper, Wong, Kapoor, Barokas, and Narayanan. Take a look at it if you'd like. So essentially that human input seems essential, right? So both in the previous case and in this case, that when I told somebody about this, who doesn't work in the domain at all, they could immediately figure out that this is a problem, right? So if you naively plug in some objective function when the real objective you want is something quite different, it can be a significant issue, right? So and the third is what I mentioned before, the CMU study that showed that if you in Google's ad settings, if you set your gender to be female, it gave you systematically, statistically fewer ads for higher paying jobs, right? So which is a representation problem, right? So okay. So so basically, there is this very nice book. It's a good popular book that you can read and give to anybody. It's called The Ethical Algorithm. It came out a few years ago. You can, for example, high school student or undergraduate could also be able to read and enjoy such a book. It's by Kearns and Roth. Came out a few years ago. And there they basically they essentially two things that come out are that you need a very precise notion of fairness to embed into your algorithm and AI system design, and typically you want so you want constrained optimization, which is that you want to optimize for overall utility subject to various constraints on fairness. Right. And also you want your training set, your training examples in machine learning. Please don't worry if you don't know this concept, but this episode E3 points out that the set of data, it's very well known, but not always followed, unfortunately, that your training data set should be broad enough to cover many important, for example, demographic groups. I just want to point out an interesting thing, which is that, so yes, we want all this fairness stuff, but just like, for instance, Arrow's theorem that you may have heard about in economics, there are some fundamental impossibility results also. For instance, there's this very nice paper of Kleinberg, Mullainathan, and Raghavan that shows that you cannot simultaneously satisfy even some simple fairness goals due to some inherent notions of boiling predictions into probabilities, right? So, and this paper is about the notion of calibration. I'll very briefly say, I think I'm running behind on time, but that's okay. This is about the notion of calibration, which is the following, right? So suppose in your weather prediction, suppose somebody says tomorrow the probability of rain in your area is 70%, right? What does that mean, right? So one way to see, how good this prediction is the following, right? Go back a sufficiently large amount of time. So suppose we keep data, historical data on say the prediction of rain, for example, or the probability of predicted rain for the next day, and then the actual the ground truth that happened, which is whether there was rain or not, right? So suppose you go back a sufficiently long period, collect all days on which the prediction for the next day was 70%, right? 70 as an example, right? And so suppose you counted, say, 1,000 such days, right? Now, by the law of large numbers, 70%, approximately 70% of these 1,000 days should have actually seen an error, right? So about 700 plus or minus a few standard deviations is the number of actual days in the past, if you kept systematic histories of what happened, where the event that was predicted, rain in this case, should have actually happened. Similarly, you can do it for various probabilities of error. So 60%, 50%, whatever, right? So if you separately collect all this data and see how well the prediction did in terms of the actual ground truth, and if you did well, that's called calibration or well calibration. And unfortunately, what Kleinberg, Mullainathan, Raghavan show is that there are inherent trade-offs of these, which to me means two things. One is trade-offs and approximations are necessary between fundamental fairness and utilitarian considerations that we want, and that society needs a strong role, and that auditing the output may be more key than restricting the input features. Since since we only have about 12, 13 minutes left for the technical talk before the questions, I will skip some of my slides. Excuse me for having to, so, okay, let me maybe just say, there is this one paper by, if you look at the first paper with the first author, Dwork, she is Cynthia Dwork, very famous and to me, personally, very inspiring computer scientist. She and her collaborators had this very nice paper 13 years ago on similar individuals being treated similarly. You can take a look at it. So let me skip this. So I spoke about having sufficient representation in your training data. Some of the work that we did in the past can actually help with this. This is using linear programming and some rigorous probabilistic methods on top of them, right? So unfortunately, I really will not have time to go over this. So let me skip over this. This is the most mathematical slide in the talk. I would have loved to speak about it, but there is more that I think may be better takeaways for you. So let me skip the further details. Maybe I'll just speak about one technical result in some detail, and then we'll skip over the rest, right? So if you go back to the beginning, we said, for example, if your entities are humans, they don't have to be, but if your entities are humans, you boil each entity, in this case a human, to a point in some high dimensional space, right? Right. So normally when we think of, say, space, we think of what is called Euclidean space, which is basically the distance between 2 points is given by Pythagoras theorem. In the plane, you know how to do it. And the same thing generalizes to high dimensions, right? So that's called Euclidean distance. But very often in data science and machine learning, the Euclidean distance, when you have these points in high dimensional space, the Euclidean distance is not the only distance of interest. There are other very interesting notions of distance called earth mover distance and so on, right? So we'll assume an abstract such distance, and such distance functions are called metrics, right? A metric is simply the following. It's a distance between 2 points P and Q that satisfies 3 axioms. First, d of P, Q is always greater than or equal to 0. The distance between 2 points is always non-negative, and it is 0 if and only if P is equal to Q, right? That is one thing. And second, you typically want symmetry, although there are some interesting functions that are not symmetric. D of P comma Q should be equal to D of Q comma P. And the third is the familiar triangle inequality, right? So you know that if you draw a triangle in the plane, and if you take any one side of the triangle, its length is less than or equal to the sum of the lengths of the other two sides, right? The same you can abstractly speak for any 3 points, P, Q, and R in any high dimensional space you want. And the triangle inequality is the same inequality. And a distance function D that satisfies these three axioms is said to constitute a metric, right? So and like I said, in machine learning, many metrics are of interest, and the Euclidean metric that we are familiar with is only one specific example, right? So we assume, yeah. So let's talk about just one thing in machine learning, in unsupervised machine learning, right? In unsupervised machine learning, for example, suppose you have you have documents from in a particular language from say 100 years ago. Nobody in a very large corpus, and you cannot systematically. There is nobody who can systematically label them as this article is about politics, this is about current events, this is about whatever agricultural or something about the economy and so on. So suppose you don't have experts to label it, this is called unsupervised learning. You have a large collection of data points. In this example, you can visualize them in this two-dimensional example. I've color-coded them as green, blue, and red. So obviously, you see three clusters forming according to whatever distance function D you're using here, right? And it's natural to assume that all the points in the green cluster are perhaps about some topic like the current economy. The other may be about warfare and international affairs from that period. And the third could be about current events, whatever, right? So clustering of points like this is ubiquitous in unsupervised machine learning, right? So the typical notion here is you're given some number k. In this example, k could be 3 or maybe 4 or something, 3 perhaps, right? So, and what you want is, given this integer k, you want to cluster your data, in this case, all these points, into k clusters, right? Such that each cluster has something coherent within it, right? So, and the typical objectives are to keep, there are various objectives you may want to optimize. And one such objective is called the K-center problem, which is what I'll focus on here, which is you want the radius according to your distance metric D of every one of these clusters to be small. In other words, you want the maximum radius to be small. Why is that important? Because if the radius of a cluster is too large, then 2 points far away within a cluster may have nothing to do with each other, right? While what you really want in a cluster, for example, if you're clustering patients according to their genome, right? If you say that two patients are in the same cluster, you really want the mutation characteristics, mutation profiles, or other such things in their genome should be roughly the same, so that you can hope that a treatment given to one patient in the cluster, or the patient in the center of the cluster, can hopefully be tried out for other people in the same cluster. So it's natural to want that every cluster should have relatively small radius, right? So, but unfortunately, individual points can be, so where can fairness fail here? Individual points can be misclassified. They could be far from their cluster centers, and even more serious, they could be cast as outliers, right? Okay, so there was some previous work, including from my colleagues Kuller and Mount. Right. So why didn't I skip over some of these in the interest of time? Not because they're not important; they're actually very important because they motivated our work. But in the interest of time, I'll directly. So without going into the mathematical detail, let me just say the following. Right. So these works assume that, suppose somebody tells you, I understand that unfortunately outliers are unavoidable in data, right? So, and if you try to satisfy every data point, right, even those that lie far away from your core set of points, then you won't be able to do anything meaningful. So I give you a budget, right? Let's say 1%, right? What I want is you are allowed to leave out 1% of your data set as outliers, but please give me, given this number k, a very good clustering of the remaining 99% into k clusters, right? So subject to not handling 1% of the points in this example, you want as good a clustering as possible, right? So, and these papers, come up with good results for these. In fact, the second paper, in some sense, gives some optimal results for this specification of the problem. But if you think about it, like the slide says at the bottom, but what about individual fairness, right? In fact, many of these problems get run repeatedly, right? And it could be that due to the vagaries of how the problem is implemented. So consider the following situation. This is actually very realistic, right? So suppose actually 3% of your data, right, could actually qualify as outliers, right? So only 97% is relatively like in the three large clusters you see here, maybe 3% lie outside. What you have the luxury of is including two, of the 3% of the total number, 2% can still be put into your clustering, but 1% has to be left out, right? But what if in repeated invocations of this of your algorithm, your clustering algorithm, and in fact this has been seen, the same types of points keep getting discarded and not being allowed a good service can have serious consequences, right? So what if among the 3% of the data set, the 1% that always keeps getting discarded can reasonably ask, why is that other 2% always getting in while we don't? While in fact, all 3%, all of us are, in fact, all of us qualify as outliers, right? So how can we get fairness? So here is one, I'll just talk about one such result that I got that we published with my former students, David Harris, Thomas Pinsel. The S in green is me and Coatrin, right? So now, here is the key point, and if there is one takeaway, here is a key way in which probability can play a role, right? So let's reformulate the problem with probability playing a central role, right? So, let's assume that as something like a service level agreement that many of you know from industry. Suppose every point J says that, I allow your algorithm to be randomized. In fact, the algorithm has to be randomized in this case. Randomness is inherent to the problem definition, right? But please cluster me. So I'm point J, right? Cluster me with probability at least my contracted value of Pj, right? So, and maybe the amount of money or whatever I pay could be an increasing function of this Pj, right? Okay, so now here we can define the problem now, right? So we allow now per user probabilistic guarantees, and we'll see some interesting consequences in the next slide, right? So so now again you're given this number k. So please look on the top, right? You're given this number k, and you're given, let's say, a maximum cluster radius r, and you want at least 99%, that is this number t, of the points in clusters. And furthermore, you want these per user probabilistic guarantees, right? So every point j wants to be so where does the probability come from here? There is no probability in the input definition. All the probability is over the random choices that will be made by whatever randomized algorithm you design, right? So so point J says that the probability that I get clustered should be at least Pj, right? And we get some what I view as useful results in this context that combine both local considerations and global considerations. Let's not parse the theorem itself, but see some of its consequences, right? Okay, so how do we interpret these probabilities? Okay, so one is, if the PJs are not given, we can take them all to be the same, right? So we can take all of them to be T over N. That's a possibility, right? The other is the frequentist interpretation. For example, if this needs to be run repeatedly, for instance, somebody watching YouTube or some interaction where algorithms like this run in the background all the time, right? So so where, for example, if you're interacting over internet ads, every time somebody does a query, a very quick auction mechanism happens in the background, right? Or if you're asking for loans from multiple agencies, in other words, if you take the frequentist interpretation, and if my PJ, I'm user J, if my PJ was 30%, I can say, you know what, I may fail in one of my trials, but if I try 10 times, I can reasonably expect to be successful around 3 times, right? So you can take the frequentist interpretation of probability. But interestingly, even for one-shot cases, in fact, this was implemented in some parliamentary context in the European Union. When I gave this talk, somebody told me about it. right? So here is the idea, right? Here is how these probabilistic guarantees can be useful even in one-shot situations. In fact, I will put it, I'll show it here, but let me just say it intuitively, right? Suppose somebody tells you that they ran an algorithm, and suppose they tell you that, you know what, you would have, this algorithm guarantees that you'll get your service or good quality of service with probability at least 30%. But of course, unfortunately, due to the vagaries of probability, you did not get it, right? Well, that black box guarantee is not very helpful because they run the algorithm and with 70% probability, and what they claim is that with at most 70% probability, I won't get what I want. With 30%, I will. But how does that convince me, right? But here is how they can convince me, right? They can run their algorithm independently a very large number of times, say 100,000 times. By the law of large numbers, very like, the number of times I'll be given service in these 100,000 would be close to 30,000, right? 30% of 100,000, right? And now, after publicly displaying the 100,000, and each of us, in fact, by the law of large numbers, and then you can do what is called the union bound over all the users J, right? All users J are approximately satisfied that they see enough times they get service. What you can do is you can take a publicly trusted lottery and pick one of these 100,000 at random, right? So if of 100,000 possibilities, I can verify myself through a simple piece of software that 30,000 of them were good for me, then I know that if I trust the lottery, then if one of them is chosen at random, then I know that really at the end, the probability that I got what I wanted is close to 30%, right? So these probabilistic, so this where I said it may not have been obvious when I said initially that probability can play a useful role. In my perhaps biased view, probability can play a very good role like this in fairness. So I think there, there are various notions of, another notion of unfairness is, for example, if you're busing children to charter schools or other such places, which is a notion in the US, it may be unfair if, two children or many children from the same street, from the same grade or standard get bused to different schools, right? So typically you want very often, similar people gain some benefit from being clustered together. So yeah, we had some works on all these, right? So again, probability plays a central role. My apologies that, in the interest of time, I'll have to stop very soon. Let me come close to conclusion by the following. The same Bertrand and Mullainathan had a very influential study in 2003 that showed that for job ads for for relatively young people, and say the teenagers, showed some, the callbacks showed some significant bias. And AI can actually greatly help with these things because, like John Kleinberg, a very influential person in this area, has pointed out in one of his talks, if you have a biased, resume filtering service, right? You can, as compared to a human who cannot easily do this, and a simple AI system can generate a very large number of sample resumes with small changes in features like, say, gender, race, whatever, right? Keeping the main content the same, but varying a few features and seeing how biased your system is, right? So on the one hand, therefore, in situations where there could be human bias, AI can greatly come to the rescue. Another very interesting thing, and this is a very US-centric thing. I know that our audience may be international, please excuse me, right? So, but there is this political notion of gerrymandering where you can slice the, congressional or legislative districts in a state, and, through rigorously defined randomized algorithms using random walks and so on, you can detect such gerrymandering. So on the one hand, I just have two simple situations where AI can actually help combat human bias, but there is also the other direction, which is interesting, right? So in bail cases, I'll go over this very quickly, but I think it's very important, right? So a judge has to make a very important decision that can change the life of a person, whether to release the person on bail for 3 months or so, pending a hearing, or to put them in jail, which is distinct from the notion of prison in the US. A prison is where a person goes if they're convicted, and a jail is where they're waiting for their hearing, right? It's a very, very consequential decision for for a person, right? What algorithms can learn and AI can learn is what some human values that may have been hard to put in, may have been hard to hard code. For example, it could be that by a study of a large number of judicial bail decisions, the algorithm finds out that the judges take a compassionate view of the parental status of the person, being, the person standing for, bail versus jail, right? So that may not have been a feature that the AI system or even a human system would have collected at all explicitly, right? It's mainly their past crime status, whatever, right? But right, by looking at a large number of past cases, we can, AI systems can learn something from, perhaps implicit human values, where, for example, you may say that, this person, has very young children. This is debatable. I'm not taking any side on this, but you could say that if the probability of recidivism or repeating the crime is the same for two patients, right? Let's say 10%, but one of them has young children and the other does not. Maybe a human would take a more compassionate view of the first one because who's going to take care of the children, right? So in other words, AI systems can learn from human values as well, human values that may be very hard to, we can't, if somebody asks you to write down your values, right? You can maybe write down your core values, but in many high stakes decisions, I personally at least would find it impossible to write down everything I consider as a core value that is important to me. But again, from mining past human decisions by hopefully responsible people, AI can mine these and actually tell us that, what, these have been flagged, these implicit values have been flagged as important. Please try to incorporate them. And again, societal discussion is essential, right? In this perhaps very rushed talk, I hope I've convinced you that AI systems can be seriously biased. But personally, I'm optimistic that with carefully crafted algorithms and human control, but not just one time, but adaptively over time, right? As the societal context changes, as the power of AI changes, all of this can mitigate both AI bias and human bias. Let me conclude with some relevant books. The first one I pointed out already. The second one, AI Snake Oil, is very recent. It's quite interesting. It's about false claims being made in the name of AI. Also, Alok Agarwal has this very comprehensive book that he released about a year or two ago on really, and for those of you who want to learn about the history and potential for AI and so on, Alok does a great job of bringing everything out. These are three potential books I'd like to put out. Let me stop here with, first of all, again, thanking all of you and happy to answer any questions.